In this video, we're going to demonstrate Bluetooth channel sounding using the latest Insight SIP Bluetooth module, the ISP2454LX. And in particular, we're going to look at how it works in a rather demanding environment. I think quite a lot of the demonstrations so far have showed this in rather idealized scenarios where you have a lot of empty space around the devices, where you're going to have the least problems, and that may not be a very realistic scenario for a lot of use cases. Maybe some, but not all, for sure. So that's what we're going to look at today. So very briefly, the product we're using here is the ISP2454LX. This is based on the latest generation Nordic NRF54L15 product. So this is an excellent new device. It's basically an upgrade in every dimension from previous generations of Bluetooth device, with a very powerful processor, a lot of memory for applications, and a large RAM, and the module has all the components you need to generate a Bluetooth signal. I won't go into a lot of detail about the product, but there's plenty of information on the Insight SIP website about that. But it's a great product, but what we're looking at today specifically is the new channel sounding feature, which is a new way of measuring distance using Bluetooth. So one of the great advantages of Bluetooth channel sounding is it comes really for free with these latest generation Bluetooth modules. You don't need any special hardware around it. It just comes with the device, really. So for the purposes of this demonstration, we're just going to use the test board that you get with the Insight SIP evaluation kit. So we're going to use two of these because it's a measurement between two devices, but there's nothing special on there really. It's just a way to power up this little board, just as a way to power up the module, and yeah, that you can access the pins on it if you wanted to do something, but there's no need to for this demonstration. And then the other end of the connection is this very same board, in this case mounted on an interface board, so we can read out some data from the module. But as I say, all we're doing here is connecting to the module to read data in and out, and then with this one, it's just sending signals back and forth between the two devices. So there's no special hardware here. What we are using is the stack provided by Nordic, the software stack, to measure, do the distance measurement using channel sounding, and we're not really altered that in any way. We're just reading out the values from that and doing a bit of averaging, and that's literally all we're doing. So it's very much channel sounding as it comes out of the box, with the software provided by Nordic and the modules as provided by Insight SIP. So what we've added to the stack as provided by Nordic is some software to read out the distance measurements as provided by channel sounding and display them graphically on a PC. So this travels via the ISP interface board and then onto the PC and is shown visually in the graphic you can see below. Now you'll see there are three different measurements, two smaller, phase and RTT. So the phase is the measurement as carried out by the analysis of phase differences across different Bluetooth channels. That's one of the techniques of Bluetooth channel sounding. And the other is round trip time. So that's the other main technique where you essentially measure the time of flight between two devices. Now what you have in a shown bigger is IFFT, which stands for inverse fast Fourier transform. Now what this tries to do is to unpack all this data from the different channels and correct to some extent for reflections and the signal not being the perfect ideal signal that you would want, and so this is the number we're going to focus on as the best, if you like, estimate of distance. Now I've just got my two boards sitting on my desk here, and you'll see that the The number is showing quite a bit of jitter. Um, what we've done is taking a rolling average of three measurements. And so there is a little bit of averaging going on, but not a great deal. And you can see that it's not 100% stable by any means. This is to some extent shows you the sort of basic one of the basic limitations of the technology, that you're not going to get a very precise, stable reading, but you do get a meaningful reading. So now we'll move on to a more structured assessment of how it works. So in order to do something a little more structured than just have two boards sitting on my desk, what I've done is I've put one end of the solution, I've just taped it up a bit crudely up on the wall, and then so that's the interface board connected into the PC with the test board sitting mounted on it, and then I've measured out on the floor, as you'll see in this little clip, a tape measure so we can see different distances. So you'll have 1 meter and 3 meters, so that's the 1 meter one there, and then across a bit further across the room you've got 3 meters. And that's pretty much the size of my home office, so you can't really go any further than that. And that's what makes it perhaps a difficult environment for the channel sounding, because it's not a big room, so there's lots of walls in close proximity that are going to maybe have reflections that could cause some difficulties for the measurement. So the first thing we're going to do is see what happens when we put two devices right up against each other, so effectively the 0 meter reading. So here we've just put the test board right up to the interface board, so you've got the two devices right on top of each other. And then if we look at then what was being measured, what you see is that you get a measurement that isn't 0, but that's arguably just an offset that could be calibrated between the two devices, that they don't, when they're at this distance, they don't measure 0 exactly. So now we're going to look what we find if we do a measurement at 1 meter. So we've got the test board over the tape measure at 1 meter, and then we're just turning it around to face the interface board with the test board mounted on it, facing about the same height. And then if we do that, then what we see is it's measuring about a bit under, in this case, 2 meters, between 1.8 and around 1.8. So if we were to assume that 0.5, 0.6 meters we saw for 0 is a kind of 0 offset that we need to deduct, then you're getting a measurement of a little bit over a meter. So it's okay, it's not bad. But as you can see, it does jump around a bit, so it's not massively stable. But you're getting a measurement about the right kind of size. So here you've got the readings then, with holding it with the in the way that will prevent the reflections off the back wall, at least to a large extent. And so what you see here is, it's still jumping around a bit, but it's not quite so unstable as the previous version. So I think, although it's hardly conclusive scientific proof, I think it is a good indication that the reflections off the back wall were probably making it behave more erratically than if they weren't there. So that's I think that's what that indicates, at least, shall we say. So as I mentioned, I think the rather erratic readings at 3 meters were probably due to the proximity of the wall behind the test board. So what I'm going to do now is just to test that theory a little bit. So before I was just holding the test boards like this, so it's going to be radiating in both directions. So instead, I'm going to hold it like this in my hand, so it can still radiate forward quite nicely, but my hand will block a lot of the signal going back towards the back wall, and so that will get rid of some of the reflection. So let's see what happens if I do that. So here you've got the readings then with holding it with the in the way that will prevent the reflections off the back wall, at least to a large extent. And so what you see here is, yeah, it's still jumping around a bit, but it's not quite so unstable as the previous version. So I think, although it's hardly conclusive scientific proof, I think it is a good indication that the reflections off the back wall were probably making it behave more erratically than if they weren't there. So yeah, that's I think that's what that indicates, at least, shall we say. So what can we conclude from all of this? Well, firstly, let's re-emphasize this is quite a challenging environment, a small room with lots of walls nearby. That's going to make it difficult for channel sounding. It'll certainly expose any problems. So it does work. It does work. We could tell the difference between 0, 1, and 3 meters. Uh, we could probably get a more stable result if we did a bit more averaging over a longer period. Obviously, that can have drawbacks depending on your use case, because even an object moving at moderate speed, you might be rather slow in getting the position. So depending on what you're trying to do, that may or may not be a problem. But it does work, but there is clearly still a susceptibility to reflections. Now let's also emphasize this is a fairly early version of the stack from Nordic. I don't know their plans for what they plan to do with it, whether they're going to do more work on it. You could probably do better by perhaps doing some work to eliminate the more obvious spurious readings. So it could potentially be improved. What we've done is pretty much taken what's there out the box and slapped it on the screen. So the things like correcting for the 0 point, which is not something that's a big surprise that you might have to do um, to account for delays in the system. So you can probably make it better than this demonstration showed, but you are going to have an accuracy at best of probably plus or minus half a meter. And if you've got a lot of things that are going to reflect the signal around, it could well be a bit worse than that. So, you can tell between 10 meters, 5 meters, close proximity pretty well. Probably you're not going to be able to do precision that's much better than that, I think, in practice, certainly in a difficult environment. If you are outside with not much around, you'll do better for sure. So that brings us to the end of our channel sounding video demonstration. We have plenty more resources about this subject. If you want to look more, we've got they're all on our website, www.insightsip.com. So there's the general Bluetooth product page, there's the product page for the module used in this demo, and then we've got white paper about how Bluetooth channel sounding works, and video resource as well about these next generation products. And there's various other materials on there, so there's plenty there to dig into if you want to learn more about channel sounding. So I hope this has been interesting. Just as a final point, I'd like to re-emphasize that if the results aren't perhaps quite as good as you thought they might be, this is no criticism either of Nordic's chip or the module that we've built around it. It really is just a question of this technology pushing what's possible in Bluetooth with its limitation of a number of channels of relatively narrow bandwidth. There is a limit to what you can reasonably expect out of this technology, especially when you have quite this quite complicated procedure of channel sounding. So it's quite clever, but it is yeah, it is going to be susceptible to some forms of interference. So anyway, I hope you found this interesting. Thank you.